Student, in this video I'm going to discuss about basically the MP3 encoding technique, but to go for that some basics about sound or audio need to be discussed. I have covered these basic things in one video before about what are the basic things to need to know about sound or audio. So sound is a continuous wave through the air and made up of pressure differences detected by measuring pressure levels at a location. So sound is created by creating some pressure in the air or medium. It might be air or it might be another medium also. So that pressure or that pressure differences need to be detected by measuring or detection mechanism or measuring pressure levels at a specific location. Microphone changes analog sound pressure to analog voltage levels. So whenever you speak through a microphone, it changes the analog sound pressure to analog voltage levels. To digitize sound, the signal must be sampled in time and encoded into numbers. So to digitize the sound, we need to convert that video voltage levels or sound levels or pressure levels by sampling it in time and encode that sampling value in time into digital values or into numbers. And also in that process quantization also involved. So quantization divides signal strength into levels linearly or logarithmically. So if you put 8-bit uh, levels, 8-bit levels or 8-bit process of storing that audio or sound, it will create 256 levels of quantization. And also if you use 16 bits, it will create 65536 levels of quantization levels. So in that numbers of levels, that signal will be divided, that strength of the signal will be divided linearly or logarithmically. How often should sound be sampled? So that is also a very important question that has been discussed in case of Nyquist theorem. Need to sample at a rate at least twice as the highest frequency, otherwise frequency is lost. That is Nyquist theorem. And what quality is required? Telephone, radio, CD, different quality requirements. For different type of medium, different type of quality of sound is required. If you use telephone, that sound quality might be different from radio quality, then different from CD quality. So depends upon the medium of it transported, the sound is transporting. Signal to noise ratio is a measure of the quality of a signal. Signal to noise ratio or SNR value is a measure of the quality of a signal. Noise may be introduced during conversion from sound to voltage. So while you convert a sound or video or sound or audio sample to voltage, some noise might be added, and due to sampling and quantization also noise might be added or reduced. There are different type of format to use in case of audio or sound, that is .au or .aiff, .wave, and of course MP3. MP3 is most popular. That is why we are going to discuss the algorithm of MP3 in a brief way. Before that, again, one more important topic, that is psychoacoustics. Actually the principles of the human perception of sound. Impact compression algorithm uses model of human hearing to remove data, perceptual coding algorithm. So try to remember these things. MPEG is actually perceptual coding algorithm. MPEG compression algorithm uses model of human hearing to remove data. So basically MPEG is introduced is a compression algorithm which remove the data which is not required or with perspective of human hearing. Frequency range is about 20 Hz to 20 kHz, most sensitive at 2 to 4 kHz. The dynamic range, quietest to loudest, is about 96 decibel. So normal voice range is about 500 Hz to 2 kHz. Low frequencies are like vowels, bass sound, or high frequencies are like consonants. Human hearing sensitivity experiment, that is an experiment, put a person in a quiet room, raise the level of 100 kilohertz tone until just barely audible. So the frequency is 100 kilohertz, but will raise that tone until just barely audible. Vary the frequency and plot. So you can see this model or the diagram here. In here actually the tone is having frequency of 1 kilohertz initially, but in that quiet room that level of 1 kilohertz will be increased uh, by varying the frequency. So experiment, again another experiment, play 1 kilohertz tone, play 1 kilohertz tone, masking tone, that is masking tone at fixed level 60 decibel, at a fixed level of 60 decibel. That is this one is the masking tone, that is this one is the masking tone, fixed level is 60 decibel. Okay, play test tone, there is another tone, that is a testing tone at a different level, example 1.1 kilohertz, and raise the level until just distinguishable, means until we might not heard that testing tone. Vary the frequency of the test tone and plot the threshold when it becomes audible. So we can vary the frequency of the testing tone and because it need to increase over the 60 decibel. So that is the point. Vary the frequency of the test tone and plot the threshold when it becomes audible. Okay, so in the previous experiment, that masking tone was not there, but actually it shows here is that increasing the value of decibel and increasing the frequency, it reacts or threshold in quiet room has been measured. But if you use here you can see, if you use a masking tone, this is a masking tone at 16 decibel, but the test tone might be at anywhere having 1.1 kilohertz, frequency might be 1.1 kilohertz, or here or anything, and raise the level. You can raise the level, means raise the level of decibel. So then try to until it might undistinguishable. Here you can see that sample of the test tone is undistinguishable because this tone is masking this another testing tone. But we can vary the frequency of the testing tone and plot the threshold when it becomes audible. So we try to test the whole or testing tone by varying the frequency, and we can see and when it becomes audible, having the masking audio also or having the masking tone also. Here you can see frequency masking. So that is a theory of masking here. Human frequency masking means some frequency of audio can mask another frequency of audio. So that is the process. So here you can see if you use different masking and different level, you can totally hide the other audio samples in that range. So actually this plot was basically for the sound to be heard by a human ear in a quiet room. So we can that actual model or original model can be masked using different frequency at different level. Okay, at different level. Okay, by we can mask that quiet room value or quiet room tone of audio can be masked using different levels of or different types of frequency sound. If we hear a loud sound, then it stops. It takes a little while until we can hear a soft tone nearby. So try to understand this. If we hear a loud sound, then it stops. It takes a little while until we can hear a soft tone nearby. Experiment. Suppose you play 1 kHz masking tone at 60 decibel plus a test tone at 1.1 kHz at 40 decibel. This is the masking tone and this is testing tone. Test tone can be heard. It is masked by the 60 decibel. So now we stop the masking tone, then stop test tone after a short delay. So if we stop the masking tone and again we stop the test tone after a short delay, so that delay value can be adjusted. Adjust the delay time to the shortest time when the test tone can be heard. Means there is a slight gap. There will be slight gap to hear the lower value or lower level of sound by removing the higher level of sound. That is 60 decibel can be removed, but after a few seconds or few fraction of a second, you can only hear the lower level of the testing sound. That is what it is saying. This is actually temporal masking. We are masking that time domain. We are masking in that time domain. That is what in the first statement is saying, that if we hear a loud sound first, then it stops. Suppose that loud sound is stopped. It takes a while. That while might be very, very minute also, very, very big also, until we can hear a soft tone nearby. So to hear a new soft tone or testing tone nearby. So that is what temporal masking. So we can combine both temporal masking and simple human masking, like this frequency masking. This is frequency masking and this is temporal masking. We can combine both. Okay, that is in the frequency domain or in the time domain. This is the masking tone. Here you can see this is the level of the tone and this is the time domain. This is the frequency domain. That is why this is the frequency value. Inaudible tones, there might be some inaudible tones because that tone is masking this inaudible tones under the curve. Again, in case of audio compression, we need to transform the time, transforming time level input signals to frequency power. Time and level means this time is simple the temporal value and level is that audio level, that is decibel value. Input signals to frequency and power. Frequency and power. So we can use different types of techniques like FFT, fast Fourier transform, or DCT, discrete cosine transform, or wavelets. All these three can be used to transform the time level input signals to frequency power domain. FFT is most popular, fast and easy, and in most numerical method text used by psychoacoustic model. DCT is often used for spatial frequency since represent linear signals better. Something similar used by filter bank. And wavelet use non-sine cosine functions for better performance on data with sharp discontinuities. So there are different type of techniques available you can use to transform the time level input signals to frequency power domain. So basic MPEG diagram is this one. PCM audio input or pulse code modulation audio input is here. Then it is divided in two parts. First, time to frequency mapping filter bank. We need to map this time domain like here. We need to map the time domain to frequency domain using some filter bank. Again, we have to follow through a psychoacoustic model. Then it will combined in bit noise allocation, quantizer and coding, means quantization will happen here. Then auxiliary data is added, that is optional, with the bit stream to create the bit stream formatting. Then it will create the encoded bit stream, means at the output that will be the compressed version of the original PCM audio input. So here first use the convolutional filters to divide the audio signal. That is 48 kilohertz sound into 32 frequency subbands. Use convolution filters to divide the audio signal. For example, 48 kilohertz sound into 32 frequency subbands or subband filtering. So 512 samples of FIFO buffer used to create this. So we can divide this original 48 kilohertz sound into 32 frequency subbands. So now determine amount of masking for each band caused by nearby band using psychoacoustic model shown previously. If the power in a band is so below the power value in a band is below the masking threshold, don't encode it. We no need to encode that music or no need to encode that sound. Otherwise, determine the number of bits needed to represent the coefficient such that noise introduced by the quantization is below the masking effect. Recall that one fewer bit of quantization introduces about 6 decibel of noise. So try to understand this. If you introduce one bit of quantization, then it will increase 6 decibel sound. So that is what important, that is determine number of bits needed to represent the coefficient such that noise introduced by quantization is below the masking effect. That noise introduced due to the quantization should be below the masking effect. So one example is here. After analysis, the first levels of 16 of its 32 bands will be like this. Suppose 1, 2, 3, 4, 5, 6 till 16, and levels of decibel. So sound levels are like for 15. These bands are nothing but like sampling. 16 samples of that 32 samples. 16 samples are here. Other 16 samples will be after that. So that is the first things. 48 kilohertz sound into 32 frequency subbands. So 32 out of 32, 16 is showing here. So for first one, the value of the decibel is 0. For the second sample, value of decibel is 8. For the third sample, value of decibel is 12. So like that, 16 groups of samples are here. If the level of 8 band is 60 dB, if the level of 8 band is 60 dB or decibel, it gives a masking of 12 dB. So we can mask that sound by 12 dB in the 7th band. 15 dB in the 9th. So if the level of 8 band is 60 dB, it gives a masking of 12 dB in the 7th band. So we can go for masking of 12 dB in the 7th band and 15 dB in the 9th band. Level in 7th band is 10 dB. So level in 7th band is 10 dB, which is 12 dB, because we are masking level is 12 dB, which is greater than the sound level, that is 10 dB. So ignore it. Again, level of 9 band, that is 35 dB, which is greater than 15 dB. So send it. So only the amount above the masking level needs to be sent. So instead of using 6 bits to encode, we can use 4 bits saving 2 bits. So here what you see, that if the value is less than the masking level, then we will not send that level. If here 35 is greater than 15, that is masking level for this one, then we will send it. Then the amount above the masking level needs to be sent. So amount above the 15 is 20. So to represent 20, we'll need lesser numbers of bits than the 35. So instead of using 16 bits to encode it, we can use 4 bits saving 2 bits. In that way we can compress the data. So layer 1, in case of MPEG layers, in the layer 1 DCT type filters with 1 frame, equal frequency spread per band, psychoacoustic model only use frequency masking. In case of layer 2, use 3 frames in the filter, before, current, next, and a total of 1152 samples are used. Models a bit of temporal masking. In case of layer 3, MP3, that is the MP3 version, better critical band filter is used, non-equal frequencies, like here, non-equal frequencies. Okay, better critical band filter is used. Critical band filter is what? Here you have seen here in this diagram. This is critical band. So there is different type of banding. This is 250 Hz, this is 500 Hz, this is 1 kilohertz, this is 2 kilohertz. So these are different band, critical band, and that is saying here, in case of MP3, better critical band filter is used, non-equal frequencies. Psychoacoustic model includes temporal masking effects. So psychoacoustic model includes temporal masking, means in the time domain also masking can be done. Takes into account stereo redundancy. So we can remove the redundancy of stereo effect, and also uses Huffman coder in the encoding process. So this is all about basics about the MP3 algorithm. So try to go through the context and also go through the literatures available in the internet. If you found or find any confusion, let me know. I'll try to resolve that over Google Classroom or Google Meet. So try to go through it once. Thank you.